4 big categories. We are going to start with the world of accelerators, which will include things like graphic cards. If you have heard about Xeon 5, which is a chip from Intel that is basically an accelerator, FPGAs, which are field programmable gates at the devices that allow you to basically change the connections during the compilation. So that's pretty cool. Francis then is going to talk about PT threads, C++11 threads, C++, UPC, MPI, co-array Fortran. And finally, we are going to just briefly mention how we can combine. We didn't discuss this year how we can combine, but it's a nice approach also to combine MPI and Openmp. So you can use MPI for message processing when you have a distributed system, and within the processor or the core or the node, you can use Openmp for trying to accelerate things locally. Okay, so let's start with. So the languages that people use in general for programming accelerators are CUDA, which is an NVIDIA proprietary language, OpenACC, and OpenCL, which are open standards. We're going to take a quick look at all of them. So let me first try to rephrase this into what is heterogeneous computing. We discussed a bit about this when we start to talk about MPI, but basically heterogeneous computing refers to the capacity of using CPUs together with other devices. It can be a GPU, a graphic card, it can be an accelerator, it can be an FPGA. The bottom line is that you try to do the best that you can with what you have. So all these techniques that we are going to be discussing today are very tied to the hardware. Unfortunately, some of them you cannot try in our systems because we don't have FPGAs or we don't have accelerators. We may have some chances to try something in the GPUs because we have a tiny cluster for GPUs, but this is very tied to the hardware. Okay, so you need to keep that in mind. You will notice that in some cases it's more complicated to program. That is also true. It's something that we can actually hide, but there may be some benefit. Just some terminology. The graphic cards are usually referred as GPU or GPU for general purpose graphics processing units. The host usually is the CPU and the local memory to that core. And the device, it can be, as I say, the accelerator, the GPU, and its memory. Usually it's way smaller than the host. When people think about the host, it's just the typical chips that we all know. The devices like GPUs most of the time look like this, a huge enclosure. But I have today something to show you. This is actually what is inside. So this is the GPU in the middle and then 4 memory banks on the side, if you guys want to pass this around. So the point is that most of the enclosure that you see there is a heat sink. So that thing dissipates a lot of things and has to be somehow cool. Okay. Some difference between the GPU and the CPU. Well, the CPU, you know, is a general purpose thing. It has task parallelism, so it can process different tasks. It tries to maximize the serial performance. It has a large memory pool, either the cache. I think we talk a bit about that, so it's very close to the central process unit, or the usual RAM. But you can see this orange region in the CPU is way larger than in the GPU. So this is a main difference. The other main difference is that so there is a central processing unit, and then there is arithmetical logical units where all the math is performed there. In the GPU, on the other hand, the data parallelism is the default thing to do. So it has thousands sometimes of arithmetical logical units that the math can be performed, and they had very tiny cache and local memory to each of these, and a very tiny pool of RAM compared to the CPU. So those are things to keep in mind, because according to that is how we need to program and how we need to instruct the devices to perform the operations. Another important difference is that some CPUs may have SIMP, which is the single instruction multiple data. It's basically vectorization. So you take an array and you can perform the addition of an array with just one single instruction. Okay, the GPUs by default, most of the things are thin or super thin, so all the operations are trying to be done at once. Okay, so this kind of super threaded that sometimes go between 500 or thousands of operations. So there is a lot of, if you have heard in the community, there is always a lot of claims that when you port your code from CPUs to GPUs, you get a performance of a factor of 50. Well, that is it's not completely true. It may depend a lot on your particular problem. It may depend a lot in the code that you are using. It may depend a lot in several things. So you need to be aware of that. The other thing that you need to be aware is that GPUs are not the most flexible device for dealing with double precision. GPUs are basically devoted to process graphics very, very quickly so that you are playing a game in your console or in your computer, so you can refresh the frame rates very, very quickly, right? And it doesn't matter if they miss a pixel or not, you will not notice when you are killing a zombie or something, right? But when you're doing compute, and so those kind of operations can be done on single precision, and there is no much things to think about. But when you're dealing with precision computation, with scientific computation, double precision or sometimes quadruple precision is needed to achieve accuracy in your results. So GPUs are not, it's not the strong suit of them in some way. It requires some level of intimacy with the hardware, you will see, and of course there is some tiny investment every time that you want to port your code to one of these devices. But at the end, it may be worth it. So the answer or the bottom line here is that it may depend. Okay? So we're going to take a quick look at CUDA. CUDA is a proprietary language developed by NVIDIA. Stands for Compute Unified Device Architecture. It has bindings with C and C++, Fortran, and others, like Python has a PyCUDA, for instance, that you can use. The compiler usually is MVC for NVIDIA CC compiler if you are using the C or C++ bindings. It's a parallel language mostly designed for dealing with the GPUs. It has a lot of nice features, but it requires a very a good knowledge of the system and how to process the information. Basically, the main thing is that you need to, every time that you want to do a computation in the GPU, you need to move your data from the CPU to the GPU because they don't share the same memory pool. And those kind of operations are the bottleneck, are the ones that are really, really expensive. Okay. So this is an example, a very, very simple example. It's the hello world. In the top, you see the C version of the hello world. And in the bottom is the CUDA version, or the GPU version of the hello world. The main thing is including the CUDA headers. And then you will notice that there are these qualifiers. They are called qualifiers, are underscore global and kernels. Those indicate basically where the code is going to be running. If it is global, it's on the device or the host device. The kernels will run on the GPU. Okay? So in this case, this first kernel doesn't do anything. These numbers here, 1, refers to the threads that we were seeing, so in which partition of the GPU are going to be running. So this is just an example. We're going to see one more interesting one. So these qualifiers can be global if it is a function that runs on a device called by the host, or host is only on the host. That's for default, by default. If it runs on the device or the GPU, it has the qualified device. Then I was talking about these numbers between the brackets. The triple brackets denote a call from the host to the device. And these values are related to the threads that are being executed to the device. The compilation process is just as usual. So you use the NVIDIA compiler. You take your file, and depending on which host and which devices is split in two parts: the part that is compiled on the host and the part that is compiled on the device. Something like that is going to happen when you do OpenCL. So in general, every time that you are doing with heterogeneous computer, you will have pieces of the code that are compiled or aimed for compilation on the host and on the device. Okay, because they had different architectures, different hardware, so they had to be compiled separately. So the kernels, in the first case, the kernel 1.1 doesn't do anything, but it can be more interesting, like trying to add 2 numbers on the CPU. So this function will try to add 2 numbers and return the value on C. So A, B, and C, as you can see, are pointers to the device memory. Okay, so they had to be allocated on the CPU. Okay, so here on the devices, nothing happened automatically. So if you want to pass information, and that is the tricky part, you need to allocate memory on the devices. Okay, so we're going to see how to do that. So this is a kind of pseudocode or steps that you need to do for in general, any function that you want to run on the device. So you allocate memory either on the host or the device. So you initialize the host data, copy the host data to the device, execute the kernel on the device, in this case, the addition of the 2 numbers on the CPU, copy the device data back to the host, so your result of the operation, output issue 1, and clean up. Clean up means release all the resources from the device and from the host. Okay? So let's see at this code how it looks. So the main function, it has 3 floats. The pointers for copying into the device, DA, DB, DC. And then I need the size of the variables I want to pass, in this case, floats. Then we are going to allocate the space for the copies on the device. So that we do with CUDA malloc for allocating memory on the CPU. We pass the content of the pointers and the size. Okay, so in that way, we are allocating memory on the CPU. Okay, so CUDA malloc allocates memory on the device. CUDA free deallocates, so we had to take care of that at the end as well. How we copy the data, so we initialize with some values 2 and 7, and for copying or moving the data from the host to the device, you use CUDA main CPI. Okay, and again is you pass the pointers where it's going to be allocated, the value, the size, and then you specifically say that you want to copy from the host to the device, and you do for A and B. Okay. CUDA main copy copies memory from device to host or from host to device. Okay, indicating here in which direction you want to. Okay. The kernel execution. So we have initialized the value, we allocated the memory on the CPU, we copy the values on the CPU. Now we can run the kernel. Basically, I'm calling the kernel add, and I pass basically the pointers on the CPU memory. Okay, and I have allocated pointer DC for the result in that case. So this one we saw before indicates a call from the host to the device, and these values, as I say, has to deal with in which or how many threads you want to execute there. After you are done there, you copy the results back to the host. So in this case, you copy DC, which was the pointer, into C. You need to specify, again, the size. If you want in some way, it's like when you pass messages with MPI, that it has to know exactly which is the size of the message and the type that you're passing. And in this case, is a copy from the device to the host. And then finally, you print. And at the end, you remove or you free all the memory that has been allocated with CUDA free the pointers that were allocated in the memory of the device. Okay, and returns it. Compilation is MVCC. It has some flags like to taking advantage of the architecture in this case. You run addition and you get basically the result out of the print. Okay, so the main message here is every time that you want to do something in the CPU, you need to move the data that you are going to use into the CPU. And that is the tricky part, and it's also It's the bottleneck because it's a very expensive operation compared with the operations that the GPU can perform. But also, as you saw in the diagrams, the memory available on the GPU is not a lot compared to the memory that the CPUs usually have. So it's a very scarce resource, and you need to handle with care. Okay, any questions from the CUDA part? If you want the result back, in that case, yeah, I think that you're asking because actually in this case, let's take a look. I was just copying the value A and B into the pointers A and B in the GPU. I wasn't copying C because C didn't have anything. C is actually the place where I'm going to put my result. And when I was done with the operation, I just copied the value of DC into C. Okay. So I didn't need to copy A and B back because I'm not doing anything. And so this is a very, very crash code in how to handle data and operations on the GPU. There are many, many other things you can do and other tricks. So this is just to give you an idea of how things more or less work. Okay. Another alternative for dealing with accelerators and graphic cards, and in particular for not the traditional kind of processing units that we do is using OpenACC. So this is a nice approach because it's a directive-based standard. You will notice that it's very similar to Openmp. It handles things basically with pragmas, kind of. And it can take advantage of GPU. It can communicate with NVIDIA, CUDA. It can deal with accelerators, FPGA, and other kind of chips. It basically put these directives like hints for the compiler, and if the compiler don't understand them, they just discard. So basically, it's the same ideas of OpenMP. Okay. Sometimes you can gain a good performance. It's portable. It's incremental, so you can start to add these things. And usually, it's something quick to do. Okay. As I say, it's very similar to OpenMP. You can see here, so we have an OpenMP code with a pragma OpenMP parallel for reduction. And then this is how it will look in the OpenACC version. Just a pragma ACC, and instead of having the parallel region, it has the kernels, because these kernels are like the idea of the threads or functions that are going to run in the accelerator or in the GPU in this case. Okay. So let's see an example. So in this case, again, I'm going to just do a times x plus y kind of routine. So the main code is just for the variable, for the vectors, allocation, and then the computation, and then the call to the routine. Okay. So basically, this is allocation of memory with mallocs, and finally here is the initialization, and then the call to the routine. So the routine that is going to be run in the accelerator, whatever that thing is, it can be the FPGA or GPU, is basically encapsulated or entitled with the pragma ACC kernel. Okay, so what it's doing there is basically using the threads to do this operation. Okay, so it will take mostly just one instruction, and in this case, you can deal with 1 million floats in a couple of instructions. Okay, so it's very simple to implement. How you compile? There is a particular compiler from ACC. You can use the ACC flag, and then if you have information about the device, it's always good to include. The compiler will generate some output for you saying which loops are parallelized and that a kernel has been generated for that particular hardware. Okay. How you run, in this case, AP run, and then -n, the number of devices that you have, and the name of the code. I didn't give a code name here, so it doesn't. Okay, so it's very, very similar very OpenMP-ish flavor. Okay. The other interesting thing, or the other approach for dealing in particular with GPUs, is you can use some libraries, and OpenACC, the directives from OpenACC can interoperate with these libraries. Okay? We're going to see some examples of the libraries that are already there, and usually more and more come every time. In the same way, OpenACC can interface with programs. That was the example that we saw before. So you can either use OpenACC for implementing some kind of OpenMP-ish thing, or you can use OpenACC for doing library calls. Okay? So there is a variety of CUDA libraries available from the CUDA developer website, and these are some examples. So there are for random number generator, for dealing with sparse matrices, for fast Fourier transforms, for sparse linear algebra, a bunch of them. In particular, if you are interested in math libraries, you have, well, I mentioned the fast Fourier transform, complete plus, sparse matrices, random number generations, performance primitive for image and video processing, a bunch of them, and more come every time. So that is also a good source of resources. In some cases, that will be enough to get some performance and to hide the complication of having to translate your code. If you get a library that can do something for you, as we have mentioned several times in the course, it's always to do that. Okay? So that is mostly OpenACC and libraries. Any questions? Yes. Yes, and with different accelerators as well. Okay. So yeah, OpenACC is a nice and easy transition into the world of accelerators and GPUs. No, it basically, when that was what I was trying to show in the when it does the compilation, if you have information about the device that you are using, it's always good to include. It's like the xhost flag that we include in the compilations on Signet. But it will try to figure out what is the accelerator and perform the optimization according to the information that it has from that. Finally, let's talk about OpenCL. So OpenCL is kind of the same idea, kind of the same flavor, but it's a bit more complicated. It's way more complicated, to be honest with you. It's usually referred as a hardware abstraction layer. So it tries to hide all the details of the hardware. But it doesn't mean that you don't need to actually code at very low level. Okay? So it's an abstraction layer that tries to hide the details and complexity of the hardware, but it still requires a lot of effort. It is used for again, graphic cards, accelerators, and usually it's designed as a middleware. So if you, at the state that OpenCL is nowadays, is usually try to refer or defer this to other applications to be used instead of your own code. So we talk a bit about the heterogeneous system. So a completely heterogeneous system may look like this. So you may have your multi-core CPU connected with a CPU, connected with an accelerator, like the Xeon Phi, or connected with a FPGA. Okay? OpenCL should basically work in this way. If you look at this diagram here, so you have your application. There is some OpenCL management that will run on the host, and then it will distribute the load of the implementation of the OpenCL to each of these devices. So you don't need to know exactly or code for any specific device. And notice here that I can be matching a GPU and an accelerator and a FPGA. Okay? The usually software stack, or it's usually called, if you focus in a homogeneous system, it's mostly like this. So you have your hardware, you have your operating system, the libraries that we use, the application, that is what we design, or the program, how we interact with the memory stack, and on the bottom you have the file system and the network if you want. When you are dealing with these devices, you will need to translate kind of what we did or move your data, as we did with the GPU, into each of these devices. So OpenCL is supposed to do or provide you tools for doing that in a less or more smooth manner than just coding for each particular device. As MPI has its own types, so if you want to move data, and this is, again, is for solving this problem of different architectures, different hardware, having a GPU that deals with integers in a way and having an accelerator that deals with integers in a different way. So you have to use the OpenCL types if you want for communicating data. Okay, so you have different types, chars, integers, floats, doubles, etc. And the thing is that when you will notice that OpenCL has different versions, it doesn't mean that the latest version, 2.0, is better than 1.0. It means just that the standards that they are dealing are different. So when you are coding in OpenCL, you need to be aware of which standard your device supports, so which standard you should use. Some examples, let's say I have a foo function, so and I want to query for an array of floats, so I can do something like that. If you see that this is very MPI flavor, as OpenACC was very OpenMP flavorish, this is very MPI flavor. In the same way, you need to allocate memory, so you define the CL type, the OpenCL type, and then you define your array. If you want to get ranges, you need to use the CL directives, and again, it's very verbose on all the arguments that it requires. One of the first things that you do always, because of this heterogeneity of hardware, is to query for the information of the device or the platforms that you're going to run. So it's going to return a CL integer type, so you get information or IDs of the platforms basically with this whole line. So as you can see, all what is OpenCL will be like very verbose, very long commands. It's kind of a pain to you. But it solves a problem that is to deal with a heterogeneity of devices at the same time. Memory allocation and memory transfer has to be done in a similar manner as we deal with the GPU. So for allocating memory, they have their own directive, CL create buffer. So you need a context. It's basically like a kernel if you want. You need the memory flags, you need the type, you need the size, and then pointers to the memories that you want to allocate. For transferring memory, you can read the buffer, write the buffer, map the buffer between different addresses, copy the buffer between different devices, and enqueue the buffer to fill with a given path. So I don't have a particular code for OpenCL because, as you can imagine, it's very complicated. But at least I want to give you the idea that it's there. You can try to use it. You probably will have to spend some time dealing with the syntax and actually how OpenCL works behind the scenes. Any questions? I think it's your turn now.
Okay, so where the graphics card stuff was really talking about hardware that we haven't used in this class at all, and won't because it's the last lecture. By the way, I should mention we're going to overview of other courses that we're giving at SciNet. One of them is it's a day course on programming CUDA. So if you want to sort of get started with that, I think it's in May. We have some separate events for that. So the next little while is just going to talk about alternative ways of programming in parallel on machines that we've seen already. So multi-core machines and clusters of nodes connected by some interconnect. So I'm going to start with shared memory programming and different ways of doing that, sort of alternatives to OpenMP. pthreads, C++ threads, Sol threads again, Silk Plus. Just to give you an idea of where some of this might be going, and some of it is already there. I don't know what your experience is, but it seems to be that everybody always feels like the programming languages out there are just not suited for parallel programming. We have to do all this extra work. OpenMP wasn't a lot of extra work, but it was outside the language, it was pragmas. Mpi was a library where you had to call library functions, and you had to be very verbose because those functions don't know anything about the program we just wrote. And so some of these are an attempt to improve this. So let's start with threading. When we did OpenMP, we were in a lucky situation where at least OpenMP does a lot for us, right? So when we started a loop and we wanted to parallelize that, we said pragma OMP 4 or pragma OMP parallel, and it spawned all those threads. Magically, suddenly I had different execution threads that did things in parallel. It assigned tasks, so portions of the workload were assigned to it. We had to give it hints on how to do it, but we didn't actually have to give each thread its task or start the threads. Now, that is great, especially if you're getting started. The same great stuff is happening in OpenACC for the graphics cards. But there is overhead in starting these threads. There is some overhead to scheduling them. Like when we did a dynamic scheduler, that actually sort of costs you a little bit. And you don't really have control over that. So there might be cases where you are more interested in doing this on a lower level. And in that case, you'll have to do explicit threading. That means you have to create your threads yourself and give them a function to do, etc. And so I'm going to look at what that looks like, because this is sort of how things were before OpenMP. Basically, you use pthreads. P stands for POSIX. So this works only for POSIX compliant operating systems, and that really means Unix and Linux. So I'm going to start with a little example. It'll just give you a flavor of the kind of stuff you have to do. But there's this pthread library that you include, pthread.h. And here's a little function that increases, that is supposed to increase a number, an integer, by 10. And I want to do that for 2 integers. Let me just say what the problem is. So there's 2 integers, both of which I want to increase step by step from 0 to 100, not to 10 to 100. So here's a function that does that, and this turns out to be the kind of function that pthreads need. So, and then I'm going to use that in the int main. So one thing that you would notice is that this function, although I want to increment integers, receives some sort of pointer of type void star. And that's because this has to be a generic interface. And so the API, the pthread, doesn't know what kind of function you want to, so it makes it as general as possible. We've seen this way back when we looked at the GSL that needed void pointers too, and we had to cast them back to what we actually want. So here, what happens is this p is supposed to point to an integer, and so I actually tell it to say, hey, this p is actually really pointing to an integer, so convert it to a pointer to an integer, and take its address, and let's put that in this reference. And then I can start using x for real and increment it 100 times. I'll print out when I'm done, and then pthread insists that I return something, so I'll just return some null pointer. I'm not going to do anything with it. That's a function that I want to give to a thread. So in int main, I'll have my first 2 variables here, x and y, and I'll print them out. And then I want to, in parallel, increment them. And I have to do something like that. So I'm going to create a thread here called th, and that's just sort of a handle, a placeholder for communicating and starting this thread. And then there's a function called pthread create that takes this handle or fills this handle, and I give it a function name as well as the argument. So this one is going to start executing this function incfunc with as its argument the address of x. So this pointer gets the address to x, gets converted back to x, gets done, and it immediately exits. That is to say, as this starts it sort of in the background, if you wish, on a separate thread, and keeps on going. It checks for any errors, but if no errors occur, the next thing that happens is that while this new thread that we just created is running, I invoke the increase function once more, but now with a pointer to y, and now y gets increased by 100 times. Then, since I can't in general know which one ends first or whether the first one's already done, I have to make sure that all these threads join together again. It's kind of the synchronization point, and that's done with this pthread join. And so it tries to see, basically this guy waits until the thread is done. Once it's done, it'll print out the values of both x and y. If there's any errors in this code, it actually captures them and says, hey, I have some error creating your thread or joining your thread, which I guess could happen, but just being careful. So it's fairly explicit. I really create this thread. I have to write a function for what it does. And I took this example from here, although it's a bit better with comments and stuff in there. And you can read some more about POSIX threads here. So if you want to compile this, suppose this code was called pte.cc. I have to tell the compiler, hey, I'm using pthreads, so -pthread will do that. And when I link, again, I'll have to say, hey, I'm going to use the pthread library. It's very similar to how we did Openmp, where we had to do the same thing. We have to do an fopenmp. If I run it, x and y initially are 0, 2 threads finish, and then after that, it's 100. And there we go. There's no point trying to see if this is any faster. This is just a simple operation. All this creating a thread is going to be kind of overhead. But it all works the same way. You create some sort of worker function that you want your thread to do. It takes some sort of pointer. You define a thread variable. You create a thread. The code keeps going, so it's parallel now. And then you join everything up at the end. That's how you used to have to do threaded programming before Openmp. And this is why Openmp is great, because you just take a piece of code, you say this part is parallel, and it starts doing it. You don't have to chop up your loops into separate functions that take a part of the loop that are done explicitly. You might still find pthread applications out there, but they're rare. And with C++11, we actually don't really need them except for very special cases, because it comes with its own threaded library. But it works very, very similarly. It's just a little bit more streamlined. So here's again an increase function that increases an integer 100 times and prints finished. And here I call it from in main. But you'll notice that what's nice is that there's sort of, it's smaller. Why is it smaller? Because a lot of the things that I had to do to convert back and forth are 11 knows about the types. It can take any sort of function in here. So we still create a thread. I give it a function, and I give it a reference to x, a reference because I want x to be actually increased, not some copy of x. So that's, and this starts it in the background. I just created that object. It starts in the background. Fantastic. While it's running in the background, I call incfunc on the other variable y, and I still have to wait for them both to finish. So there's a join, and then I print it. So the compilation is very similar, except I don't have to worry about pthread. It'll actually probably on Linux use pthread under the hood, but that's up to the compiler to deal with. So I just have to make sure that I do compile with C++11, because this is a C++11 library, and it works the same way. So that's basically the same thing, but just a little bit less for both. And this is only the start of what C++11 threads can do. So there's some other things it can do, such as accept basically in-line definitions of functions. These are called Lambda functions. We have not looked at them, but they can be very useful in this case. You could just have a piece of code, and now if you want to thread it, you have to write a function for it. Well, that function definition can actually just be in line where you call the code. You can have things like asynchronous tasks, so you can spawn a task, and you can ask it to return a value sometime in the future. So future values. You can have atomics, mutexes, locks, very similar things to Openmp. You would still not use this where Openmp fits, but you might use this in cases where you have very varied tasks to do. Maybe you're writing something that has a GUI and is writing to disk. It also communicates over the network. Those things are kind of cumbersome to do with Openmp. It's possible, but it's still cumbersome because it's not loops. So doing threads might be a little bit easier. So it's in the standard, and that's why I wanted you to know about it. And it kind of looks like threads. There's another variant of this, which I won't go into too deeply. It's sort of a language extension called Silk Plus, but it's C. Oh, there's a C++ version now too, I think. The point here is that it tries to become a language. So threads and threads still are libraries, right? They're kind of built into the language, but not really. This is a language extension. It just adds 3 keywords, spawn, sync, and for, with Silk in front of it. You can imagine the first one spawns a thread. The second one waits for a thread, so it's kind of like the join that syncs things. And the for is the only thing that isn't in the threaded one, sort of is a Openmp for replacement. So you can just do some work loading. Now, it has a bunch of functions that are actually kind of ugly because there's lots of underscores in them for reductions and other things. So you can program this using those functions. So saying that it is just 3 keywords that are added to language isn't really true. And then everything becomes a task, and so everything is handled by a scheduler. So this is good and bad. If you have a very regular workflow where everything is chopped up and you didn't have to play or tune your Openmp, this isn't going to make it any faster. But if your stuff is very load imbalanced or you have lots of little things to do, this has a pretty decent scheduler, and so this could be something to look at. It's supported by, I think, the Intel compilers, so you'd have to work with that. Part of it by the GCC compilers, but not everything. So that's why I sort of skip it. So these are some alternatives to threading, but they're still only running on a single node, and of course, that's not what we want. But it's a nice, this idea of spawning threads, of having shared memory, is very nice and convenient. And you've noticed probably how much more cumbersome an MPI homework is versus an Openmp. So there are attempts to fix that too, to sort of get to languages where we don't have to do all this explicit message passing, bundling things up, receiving it on the other hand, make sure things aren't deadlocked. And they go under the name of PGAS, which stands for Partitioned Global Address Space. I didn't even spell it right there. So here the idea is to try and treat the distributed memory more as if they were shared memory. The idea is, yes, the memory is distinct, but I can still address it. What will happen under the hood is somehow a runtime goes and grabs the relevant piece of memory. So if I build it into a language, I will have to say in the language which parts of my memory are local and which are not, which are shared but remote and which are just plain ones. And so you'll find that that's the balance you strike. Yes, you can extend some of the languages like C and Fortran to do this, but you'll have to still say what is local and what is not. And you'll have to realize that if you address a piece of space that is far away, that is more costly than close. So one of those, a fairly mature one, but not very much used, is called Unified Parallel C. Unfortunately, it's C. It's a little bit old, not C++. But it defines basically a way to distribute your data. It kind of works like this. There's this variable threads, or this constant, always define how many there are. And if you declare an array that is shared, it basically distributes it over all of the processes. So it's complicated or confusing because UPC calls its processes, the MPI process equivalent, threads. Although they're now exactly what we called processes before. So these threads can't easily get each other's memory, but by calling it shared, they can. Basically, there's some way where the runtime gets Y0 from process 1 whenever it needs to. It can have higher dimensional arrays, or I can have an array of 100 in each of the threads. And so basically this last index is an index along the threads, which are really processes. The way this is implemented is really a translation model. It takes this C and translates it to C, calling all kinds of MPI stuff under the hood. And the most common one is the Berkeley UPC compiler. And so it does that, it translates that, and then it compiles it with with the other compilers. So this is what it might look like. Say we want to add 2 arrays of size n. Actually, n is 100 times the threads, which means that each thread gets 100 to do. I can do this just by defining them as shared and by making sure that I only update when I am in my thread. There's better ways to do it, but this is essentially what you do. So this basically gives gives a role. So every next element in this array is assigned to a different thread. You can question whether that is wise, but that is the default way. And so when you compile this with module load Intel MPI UPC and the UPCC compiler, and you run it with 4, it will run. It'll say, because it also has a little print statement here, I from thread 0 to 1, 3. Very much like an MPI process, except I didn't have to do any of the sending, right? So all of this is sort of automatically done. It does the different parts. Now, I'm not sending here anyway, because I have not initialized this. This is a horrible, horrible example. But you can get the gist of this. I can get to the other memory, but under the hood, it's still all MPI. Secondly, our current UPC module is old and doesn't work with the Intel compiler anymore, so I can't even really have you try this out. If you want to, you can either install UPC or we can install a new one. But that's so. This is one of the ways to try and improve. A second way, or the last way of today, is co-array Fortran. Fortran, yes, Fortran. Fortran is easy to read as a language, and so I'm not too scared to tell you that this thing exists. But for every array that can have multiple dimensions here of 100 by 100, co-arrays in co-array Fortran can have an additional one that gets square brackets and has this star in it. It says, I'm going to launch you with a number of processes, and the star means I just divide them over that's an extra dimension over the processes. So every process gets this array on its own. And then with that extra last dimension, I can address those other processes. So yes, Fortran, there's no co-array C++. Well, it's not true. Cray makes a co-array C++. It works very, very similarly. But that's not a free compiler. You have to have a Cray system to work with that. Who knows, one day this will be in C++. But this is kind of what it looks like. I have an integer. It looks like a single integer, but it has this codimension, which means every image has one copy of it. And I can get other copies just by saying A1. This is A from image 1. And so image 2 is basically getting the value of image 1. But, and so I can module purge. This actually works with the Intel compiler. And I can run, and one of the images got this value 11 to itself, and then printed 11. For this to work well, this is sort of the crux of all of this shared memory stuff. So you have to say what is shared and what's not, what has a codimension and what is not. But you also have to sync. You have to say when things have to be aligned where, and if you don't, you're not going to get a correct program. So where in MPI, the whole game is to send the right messages to the right neighbors at the right time. In these sort of PCAS languages, the whole game is what is shared, what is not, and where do I sync? And you have to be careful, because if you sync too often, you basically serialize your code. You're just waiting all the time. This is all based on MPI 3's, well, most of it, one-sided communication. So if you want, you can do it with MPI 2. It gets very complicated. But you don't have to use these language extensions. So you could write your own little co-array Fortran in C++ using this. And then I won't mention anything but saying that all these techniques can be combined. And most commonly, one combines Mpi and Openmp. So this is a little picture. Here are my nodes. I have 4 cores. Would it not make sense, since they are sharing the memory, to do these 4 cores with Openmp, and then among the nodes you do Mpi? Yes, that would make sense. And usually that is a little bit faster, because making a thread is lighter weight than making an Mpi process. And so you just include all of the headers, you Mpi init, and you pragma Omp parallel 4. Just mix and match. The only thing you have to be aware of is that when you're actually launching these things, MPICC, Openmp, everything, just mix it together. When you run it, you have to make sure that things get divided as you expect. So you don't want, if you had, say, 4 nodes, you don't want 4 processes to be started on node 0. And then all those processes start running 4 or 8 threads. Now you have 32 threads on one node, and the others aren't used. So you have to make sure that things are done. So Mpi run doesn't know that you want to do this. It doesn't know that your executable is threaded. So you have to say, well, divide things up by node, and then it makes sense, because I'll get each node gets an Mpi process, and then they can start its task. So it's important to do this right, but it's not very difficult. And from a programming point of view, it's really easy. I promised you in the beginning. So if you want to know more about either CUDA, or we're going to have some Python, you want to do more practicing with your Openmp and Mpi, there's a summer school that we'll be giving in July. We'll have some other interesting topics. We actually have databases and large-scale I/O courses coming up too. And all of that you can find on the education site. Questions? All right. Oh, yes. Before so fill out the survey or the course feedback that you should have gotten from the university. If you're enrolled, you should have gotten it. Okay, good. Yeah, we'll post the homework later. So there'll be one more homework, doing something with I/O, and we'll post that later today. Save. Yes.